We're now going to take a look at one of the fundamental concepts of linear algebra, and the name of that concept is linear independence, right? Now, there is a distinction between matrix algebra and linear algebra, and we're kind of straddling that line right now. I mean, most of what we've done up to this point is considered matrix algebra, all the manipulations, all the operations that we've been doing. Now, linear algebra focuses more on general concepts, more abstract ideas. But just because an idea is abstract, it doesn't mean it fails to have any practical significance, right? So before I give you the formal definition of linear independence, let me use a little example just to kind of motivate where we're coming from. Like why is this even, worthy of study, right? So let's consider these three forces. So consider, let's say F1 is the vector, I'm just using F for force. Say it's the vector 3, 2, 1. F2 is the vector, let's see, that one, say -1, -6, and 2. And then F3 is the vector, let's say -4, 8, -6, right? So here are three forces, and these are all three-dimensional vectors, so that means they live in R3. And before we start to get into the algebraic stuff, let me actually, just give you a quick little glimpse as to how you can sketch these three vectors. So what I'm drawing now is X, Y, Z coordinate system. Now, the idea is that these axes are all perpendicular. This one, which is often used to represent the x-axis, is actually supposed to be coming out of the screen at you, right? But obviously we can't do that, although I could see some virtual reality stuff. That would be really cool. But since we don't have that virtual reality stuff, we're going to have to use our imagination and have this axis, coming out of the board at you. And then the axis going due north is typically your z, and then the axis going due east, that's your y, right? So the point at which they all meet, that's the origin, so that will be 0, 0, 0. And then the arrows indicate the positive direction for each variable, right? So let's say I wanted to sketch the vector 3, 2, 1. So that means I would have to go 3 units in the positive x direction. And again, I'm not going to put any markers there. This is just a sketch. I'm just going to count it off. 3, or 1, 2, 3. And then from this point, go 2 units in the positive y direction. So that's 1, 2. And then from this point, go 1 unit up, 1 unit in the positive z direction. So let's say we go up this way. So then this is the vector F1. My arrowhead there isn't that pretty. Let's make it a little bit prettier. There we go. So there's my vector F1. F2, now it has a -1 x coordinate. So that means I'd have to go 1 unit back through my board, right? So it's like 1 unit in the opposite of this direction. So 1 unit back, so let's say 1. And then 6 units in the negative y direction. So again, let's count it off. 1, 2, 3, 4, 5, 6, so roughly there. And then 2 units in the positive z direction. So 1, 2, so roughly that point. So I'm drawing all these vectors with an initial point at the origin, and I'm just kind of estimating where their final point would be based on the components in the vector, right? And then finally, let's sketch F3. So F3, now 4 units in the negative x direction. So say 1, 2, 3, 4. 8 units in the positive y direction. So 1, 2, 3, 4, 5, 6, 7, 8. And then 6 units in the negative z direction. So I have to go due south from this point. 1, 2, 3, 4, 5, 6. So roughly there, right? So then let's draw our vector again, starting at the origin and ending at that point, right? So let me label all of these. So this is my F3, this is my F2, all right? Now, again, if I'm referring to these things as forces, one of the fundamental things as far as forces is to find a resultant vector. Well, the resultant vector, once you have your vectors in component form, is simply the sum of these three, right? So if I use F sub r to represent the resultant vector, right? So the resultant vector, well, that would be F1 plus F2 plus F3. And then many times, in terms of physical systems, you want the resultant vector to be 0, right? So we would like this vector to be equal to 0. Well, let's see if that's the case for these three vectors. Well, so if I take, so all we have to do is add the corresponding components. So adding the first components would be 3 plus -1 plus -4. The middle components, the y components, would be 2 plus -6 plus 8. And then the z components will be 1 plus 2 plus -6. All right? Well, just performing our basic vector algebra, we end up with, what do we end up with here? A -2 in the first component of our vector. And then in the middle component, we have a 4. Yep. So 10 minus 6, so that's 4. And then the third component, or z component, that's going to be -3, right? So yeah, that's the resultant. So this resultant is not the zero vector. The zero vector, right? So zero vector is sometimes denoted like this, but in component form, it's just the vector where all the components are equal to 0. And clearly that's not what we have here, right? So, okay, so these forces don't result in a zero vector when added together. So then let's modify the question and ask a slightly different question. Suppose we had the ability not just to add the three vectors together, but what if we could scale the vectors, make them longer, make them shorter, but keep the direction the same, right? So what if we could modify the magnitude of each vector, but not the direction, right? So again, by that we mean, so for instance, and I'll just use one of these vectors as an example. If I, for instance, were to take a constant times f1, well, depending on what this constant is, I might be making the vector f1 longer or shorter. So, for instance, if the constant is bigger than 1, then this increases the magnitude and it keeps the direction the same, right? So if your constant is greater than 1, then this leads to a longer vector pointing in the same direction. So longer and same direction, right? It just lengthens it. So like, for instance, if my constant is 2.5, then I would multiply each component by a factor of 2.5, thus making the magnitude greater. If the constant is greater than 0 but less than 1, then it will be shorter. So like if my constant is a half, then I would reduce the magnitude by a factor of 1/2, right? So if my constant is between 0 and 1, then this vector is now going to be shorter than the original vector But again, it will be in the same direction, right? And I'll just state this. I'm not going to write down, there are really two other possibilities, but I'm just going to say this. If my constant is negative, then that will change the direction. So instead of F1 pointing this way, if I were to multiply by a negative constant, it would point in the opposite direction, right? So I'll just say opposite direction. It could be either longer or shorter depending on what negative number I multiply by. So this will lead to a vector that's now pointing, that's oppositely directed to F1. All right. So that's essentially what we want. We want to multiply each of these vectors now by their own scalar, such that when I add the scaled vectors together, can I get the zero vector? So let me write down algebraically what we're asking, right? So can we find these constants? So can we find scalars C1, C2, and C3, right? So are real numbers such that C1 times F1 plus C2 times F2 plus C3 times F3, that gives us the zero vector, right? So again, just to reiterate, we know simply adding the vectors as they're given to us does not create the zero vector. It doesn't result in maybe some form of static equilibrium, right? But what if we could lengthen or shorten the vectors, or maybe even have them go in opposite directions, right, of where they're currently pointing, and get the zero vector, right? Now, if you look at this question, you might say, well, I think I have a clever solution. What if I just choose all the constants to be zero, right? So what if I multiplied all the vectors by zero? And then for sure, their resultant would be the zero vector. So it is a clever solution, but it's what we call the trivial solution. So let's make a note of that. So obviously, right, in a very condescending way, obviously, clearly, C1 equals C2 equals C3 equals 0. So if I choose all my scalars to be 0, then these values for a constant satisfies this equation, right? So these, they satisfy this vector equation, right? And we refer to this as the trivial solution, right? This is called the trivial solution, right? But again, what if this represents a physical system? Like these are actual forces in some physical system. Then we don't want to trivialize the system, right? So we acknowledge that this is a solution, but again, we demand more. Like we the people, we demand not just having zeros being added up to give us the zero vector, right? No, what if we want a non-trivial solution? So is there a non-trivial solution to this, right? So is there a non-trivial solution, right? Well, I mean, we have an equation, right? And we know how to solve lots of equations. So let's put some detail in this equation, right? So I'm gonna, oh, I forgot my little one there. Keep forgetting some of my subscripts. So we have the component form of the three F vectors, right? So let's actually write this down. So what we're asking is, can we find constants that are not all zero that would satisfy this vector equation, right? So there is F1 and F2, -1, -6. Let me scroll back up and see. I think that was a 2. Yep, that's a 2. And then plus C3 times, and then we have the -4, 8, -6. And again, what we would like to result to be is the 0 vector, right? Well, previously, when we were working with those linear combinations, we turned the vector equation into an augmented system, right? And see what it looks like. So for instance, if I do go ahead and do my scalar multiplication and my vector addition, this is what I end up getting on the left-hand side. I'll have 3c1 minus c2 minus 4c3, and then I'll have 2c1 minus 6c2 plus 8c3. And then from the third components, I'll have c1 plus 2c2 minus 6c3, right? So this is the vector, right? This is the resultant now of the scaled vectors, and I want that to be equal to the 0 vector. But again, if you think of in terms of matrices, right? Then this component would have to be equal to 0, this component equal to 0, this component equal to 0. So look, we have ourselves a linear system. And it's not just any old type of linear system. What we have is actually a homogeneous linear system. Because look, the constants on this side are all 0. Right? So we have, in fact, let's go ahead and write this now in augmented form. Let's put this in augmented form. And then my coefficients are 3, -1, -4, and then 2, -6, and 8, and then 1, 2, -6, right? I mean, and look at it, and notice what we did, right? So our 3 original vectors, they just end up being the columns for the coefficients, right? That's clearly obvious, right? They are the columns, and they are the coefficients. And then the vector, our 0, 0, 0 wish, it just ends up being where our b's normally end up. So what it comes down to is, in order to find a non-trivial solution, this system would have to have at least one free variable, right? Because we're going to go ahead and do it, but I just want to kind of preface what we're about to do so we know what we're looking for, is if we end up with 3 pivots, right, 1 in each column, because we're only going to have zeros on this side, it would mean all my constants would have to be equal to 0, right? Right. Let's actually make a note of these two things. Let's write this over here before we actually go through with the process, right? Because I think at this point we're all pretty good, if not very good, at our Gaussian elimination, right? So let's actually formulate why it is we're going to do this. Not just because, okay, we have a system, but let's really think about it. If this linear system, right, so if this system has a unique solution, then it means that solution is only the trivial solution, right? So if this system has a unique solution, then C1 would have to be equal to C2, it would have to be equal to C3, and unfortunately they would have to be equal to 0, right? Because what this would mean is, so this is because we would end up with 3 pivots there, and then using back substitution, all our variables would be 0. So this is because having 3 pivots, let's say having 3 pivots, right, means all variables would have to be equal to 0. So all variables are 0, right? Now, so if we want a non-trivial solution, it means we would have to have something that's different from all the constants being 0. But because this is a linear system, remember, there are only 3 possibilities for the solution set of a linear system. No solution. Well, we can rule that out because we know we have the trivial solution. We could have a unique solution, right? Which is, again, what we don't want. Because if we have a unique solution, it means that it has to be only this. So then the only other possibility is what we would love to see is that this system has at least one free variable, right? So let's write that over here. So if this system has at least one free variable, then we are guaranteed to have a non-trivial solution, right? So then, and not just one, but actually infinitely many. So then, but I'll say then a non-trivial solution exists. And we would be able to find constants that aren't all 0 that would satisfy this, right? Again, we know the trivial solution works. Are there other ones? But because of the nature of a linear system, we can't just have like 2 or 3 solutions. It's either 0 solutions, 1 solution, or infinitely many. All right, let's go through our process here and see if we can figure out which one it is, and then maybe find this non-trivial way of combining these vectors to get the 0 vector. All right, so let's to solve this, I'm going to try to get a pivot up here. So let's swap rows 1 and 3. So we're going to do a row swap like that, and that puts the 1, 2, -6 in the top row. And then the 2, -6, 8, 0 stays in the middle, and then the 3, -1, -4 goes in the third row, right? So now let's go ahead and use our process of Gaussian elimination. So I'm going to take -2 times row 1 added to row 2, and then -3 times row 1 added to row 3, right? So I'm using this as my trusty pivot. All right. Well, with these two operations, the first row will not change. But now, so doubling, well, multiplying this by -2 and then adding here, I end up with 0, and then a -10, and then a 20. Right, see, that's 20. Let's make sure that's right. So that's it's -4. Yeah, and then on this side we'll still have 0, right? Then let's do this to eliminate the 3. So -3 plus 3, that's 0. -6 minus 1, that's -7. And then what do we have here? 18 minus, so I'm sorry, 18 minus 4, so that's 14, and then that's 0. All right. Now, if we multiply the second row by -1/10, right, now to get a pivot right here of 1, right, so if we do -1/10 times row 2, and then looking at the third row, I notice these are also, so in fact, let me go ahead and do this. Let's do -1/7 times row 3. Again, we can do those together. So we have 1, 2, -6, 0, and then we'll have 0, 1, and -2, 0, and then here we will have 0, 1, and again -2. And this is the thing that we recognize going back to linear systems. When you end up with two identical rows in your system, it means you can now eliminate an entire row, and once you do that, we have our free variable. So it turns out it is possible, right? So let's go ahead and do it formally. So if we take -1 times row 2 and add it to row 3, we end up with 1, 2, -6, 0, 0, 1, -2, 0, and now we end up eliminating every entry in the third row, right? So that means C3 is actually a free variable. Let's go ahead and write down the solution to that this system parametrically, right? So it's been a while since we've done this, but again, this is one of these fundamental things that you end up doing a lot in problems like this. So let C3 be equal to t, some real number, right? Then this tells me that C2 will have to be 2t, and then C1 would have to be so negative. Okay, let me write this down. So this will be -2 times 2t, and then a plus 6 times t, and then that gives me, what's that, -4. So also 2t. Here we go, right? So here is our parametric solution set for my constants. It's any triple of constants of this form: 2t, 2t, and t. Right? So again, so what does this mean for my vectors? Well, let me now write down the vector equation again, and I'm going to put some blanks in front of the three vectors. So 3, 2, 1, and a blank, right? And then -1, -6, 2, and then another blank, and then our -4, 8, and -6. So this is saying that we can pick anything for C3. So I'm going to go ahead and pick 4 here, right? Then whatever I pick for C3, I have to double it, and that has to be my C2. So if I double this and make this 8, right? And then similarly, whatever I picked for my t, I would have to double it, and that would have to be my C1. So if I put an 8 there, right? Then let's see if this combination now results in the 0 vector, right? So let's do our scalar multiplication and then addition. So what do we have here? We have 24. And then I have -8, and then -16. Hey, that's 0. Let's check the middle component. I have 16, and then -48, and then +32. Hey, that's also 0. And then for the last component, we have 8, and then 16, and then -24. And lo and behold, there is our wish come true, right? Must be Christmas. So what we found now is that there is a way to combine those three vectors in a non-trivial way. So in other words, you make this vector 8 times as long, you make this vector also 8 times as long, and then if you make your third vector 4 times as long, they will result, right, when you resolve them, or when you simply add them all together, we end up with the 0 vector. And and this is showing that it's not just 4. I can put any number here. So for instance, again, this is another important way to interpret these parametric solution sets. Whatever number I put here, as long as I double it here and here, it will work. Let's actually do it with the letters T in there to see that they still resolve to 0. So if I do, I'll write these down in red. So if I take the 2t and multiply the first component here, I'll have 6t. Multiply this component here, I will have negative 2t. And multiply this component here, I'll have negative 4t, right? If I take the 2t and multiply the middle component, I'll have 4t there, and then minus 12t there, and then a 8t there. Then finally, if I take whatever this 2t ends up being and multiply the 1, I'll have 2t. Multiply the 2, I'll have 4t. And then multiply the negative 6, I'll have negative 6t. And look at that. It doesn't matter what t is. They all simplify to 0. So 0, 0, 0, right? So we found not just one non-trivial way to combine these three vectors to get the 0 vector. We've found infinitely many. If I put a 10 here, I could put a 20 and a 20 there. If I put a negative 5 here, I could put a negative 10 here, a negative 10 here, and it would still result in the 0 vector, right? So keep this in mind now that we've done this example, and again, I'm going to use this, the fact that we were able to find this non-trivial set of solutions to this vector equation is what is the defining characteristic of linear independence / linear dependence. All right, so let's write something down. Right. So let's say given a set of vectors in Rn. So let's say my vectors are v1, v2, vn. Actually, let me write this here. This n should be a superscript. And let me not use the same n there because it doesn't have to be the same number of vectors. You could have more or less. So let's use something like m, right? There we go. So given a set of vectors in Rn, if the equation, so if the following equation, and here is the equation if I take C1 times V1 plus C2 times V2 plus plus Cn times Vn. If this equation has non-trivial solutions like the one that we came up with up here, right? If we can find non-trivial solutions to this vector equation, these vectors, this should be m and m, then these vectors are said to be linearly dependent, right? So if this equation has non-trivial solutions, the vectors v1, v2, Vm are said to be linearly dependent. Are said to be linearly dependent. Right? If we went through our process and if we didn't end up with a free variable, and if the only solution to this vector equation is the trivial solution, then the vectors are said to be linearly independent. So if the only solution to this vector equation is the trivial solution, right? And let's remind ourselves what the trivial solution is, where all the constants have to be equal to 0, right? If the only way that we can combine these m vectors and get the 0 vector is by putting a 0 in front of each of our vectors, then v1, v2, vm are said to be linearly independent. Right? Are said to be linearly independent, right? And that's our key definition. And it comes down to what type of solutions do we have for this equation, all right? Now, let's do another quick example just to show you how this works. And then, so basically, what this shows is that those three forces that we started with earlier are linearly dependent because we got lots of ways to combine them, right? Now let's look at this other example. Right? And the thing is, we have to be able to answer this question regardless of the dimension, whether the vectors are 2D vectors, 3D, 4D, 1000D, which isn't going to happen, but in principle, it's possible, right? So here's the question: are the vectors? Let's say here's my v1. Let's see, 1, 0, 1, 2. Right, v2 is a vector 0, 1, 1, 2, and v3 is the vector 1, 1, 1, 3. Right? Are these vectors linearly independent or linearly dependent? That's our question. And then we are going to have to justify or explain, right? Okay. So again, just using this definition, what we have to try to do is to see how many solutions do we have to that special homogeneous system, right? So to answer this, we have to see if we can find non-trivial scalars that would satisfy this equation. Right? That's what it means. And notice we have three vectors here. These are four-dimensional vectors. They're 4D because they have four components to them. And then what we would like to get out of this is the 4D zero vector. So can we find non-trivial constants to satisfy this? All right. Well, let's convert this to a linear system. Let's go straight to the augmented form. The augmented form would have this as my first column, this as my second column, this as my third column, and then we'll have our usual fence, and then the zeros would make up my fourth column. Right? That's the augmented system. So let's see what would happen. What if we tried to reduce this? Well, we have our pivot there. So let's do negative row 1 added to row 3, and then negative 2 row 1 added to row 4. Right, what are we going to get? Well, the first row will stay the same. So will the second row. That won't change. Third row now, I will eliminate that entry, and this one stays the same, and I would eliminate this entry as well, and then that's 0. And then let's see, eliminating the 2, this 2 will stay the same, and then we'll have a 1 there, and then that will be equal to 0, right? So this would now be our pivot, right? This would be our pivot. And we could go ahead and eliminate this, but if you notice, this equation right here tells me that C2 has to be equal to 0, right? So we could continue doing our elimination, but just recognize that this third row, because it has only one entry in there and it's already a 1, this tells me that C2 has to be equal to 0. So if I plug that now into the second equation, let's say I did my back substitution here, even though this is not in an echelon form, I can start to see what the solution is going to be. So if I go to my second row, this tells me that C2 plus C3 is equal to 0. But if C2 is equal to 0, then this means 0 plus C3 has to be equal to 0. So C3 has to be equal to 0. And then if C3 is 0, I can go to my top equation, because this tells me that C1 plus C3, that has to be equal to 0. But if C3 is 0, then C1 plus 0 is 0, so C1 is equal to 0. So what this shows is that the only way I can combine these three four-dimensional vectors to get the four-dimensional 0 vector is if all my constants are 0. So because of this, right, so since this system has only the trivial solution, right, so only the trivial solution, then these three vectors, so v1, v2, and v3 are linearly independent, right? So they're independent in the sense that there is no way to combine them together. Even if we try to scale them using any constant, we can't get the 0 vector, right? So hopefully this video, starting with that example of physical forces and wanting to resolve them in such a way that their resultant is 0, kind of gives you a motivation for the definition that we gave for linear independence and linear dependence. But what it comes back to, unsurprisingly, is how many solutions do we have to a particular linear system, right? I'll see you in the next video when we expand on these concepts.